Hi, in this video we solve question number 18 of IIT JAM 2021 mathematics paper. Here's the problem. We have a function f of x defined piecewise like this. There are 4 options out of which only one is the correct answer. The option A is about strict local minima of the function and the rest of the options are about continuity of the function. To answer this question, let us examine the given function more closely. In the first part of the definition, the given set is the set of irrational numbers including the 0, where the function is defined to be constant 1. In the second part, the function is defined over all non-zero rational numbers in the following fashion. It uses a unique representation of rational numbers where any non-zero rational number x can be written as n by p for some non-zero integer n, and a natural number p such that the GCD of n and p is equal to 1, meaning n and p have no common divisor. So, to sum things up, the function is a constant 1 for all irrational numbers including 0, and at rational numbers it is defined as 1 minus 1 by p for this given representation of rational numbers in terms of n by p. So we see that the function has interesting definition for non-zero rational numbers that depend on p. So what we do is, in order to understand the function more closely, let us examine the rational number representation in terms of p. It will be clear then how this function behaves on these numbers. Now for p equal to 1, these rational numbers can be written as plus minus 1, plus minus 2, plus minus 3, and so on. For p equal to 2, you have rational numbers plus minus 1 by 2, plus minus 3 by 2, plus minus 5 by 2. For p equal to 3, you can write them as plus minus 1 by 3, plus minus 2 by 3, then plus minus 4 by 3, and so on and so forth. Very good. Here's a quick demonstration of these rational numbers over a real line. Suppose you have this real line, 0 is here. Then for p equal to 1, you have plus minus 1, then plus minus 2, and plus minus 3, and so on. So these are rational numbers corresponding to p equal to 1. Similarly, you have rational numbers corresponding to p equal to 2, like this. Similarly, you have rational numbers corresponding to p equal to 3. And so on and so forth. So this representation of rational numbers in terms of p equal to 1, 2, 3, 4, etc. gives us a nice way of embedding rational numbers or real line in layers. The first layer is for p equal to 1, the second for p equal to 2, third for p equal to 3, and so on. Very nice. Now that we have noted these things, we note the following critical observation about these rational numbers. So what we are interested in is the distribution of these rational numbers as functions of p. As noted above, the rational numbers for each layer p are discretely distributed along the real line. Let's make this notion mathematically precise. We have that for fixed p, if we take two rational numbers, n1 divided by p and n2 divided by p, take their difference, this is equal to n1 minus n2 modulus divided by p, and if n1 and n2 are distinct, then this difference is greater than or equal to 1 by p. Now what this tells us is the following: between any two rationals with fixed p, there is a minimum gap of 1 by p. So in each layer p, the rational numbers are distributed along the real line with a minimum gap of 1 by p. So they are discretely scattered. This is the meaning. Very nice. Now this also means the following: for every real number x, the unit interval around x contains only finitely many rational numbers for a given fixed p. Very well. Now let us examine each of the given options. Option A says that if x is a non-zero rational number, then it is a strict local minima for f. Here's a nice intuition regarding the behavior of the function. You see, as function of rational numbers, it is defined as 1 minus 1 by p, and 1 minus 1 by p goes on increasing as you increase p. In other words, with every layer you put in the number line, the value of the function is increasing. So in a way, your function is locally increasing. Let's make this notion mathematically precise and see what's going on. So consider any non-zero rational number x given by n naught divided by p naught, so that its functional value is 1 minus 1 by p naught. Now about x, we know from earlier that if you consider this unit interval around x, then there are only finitely many rational numbers with p equal to 1, 2 up to p naught. Now let us represent these finitely many rational numbers using these crosses and consider a smaller neighborhood around x that avoids all these crossed elements. Mathematically, it means that you get a delta positive such that for every y in the delta neighborhood of x, y is either an irrational number, or y is equal to x, or y is a rational number of the form n by p, where p is greater than p naught. So locally, if we have y not equal to x in that interval, then f of y takes two values. It is equal to 1 if y is irrational, and it is equal to 1 minus 1 by p if y is a rational number depending on p. Now, since by choice p is greater than p naught, what we have is 1 minus 1 by p is strictly greater than 1 minus 1 by p naught. And 1 minus 1 by p naught is the functional value of x. So in other words, we have f of y greater than f of x whenever y is not equal to x. And it means that x is a strict local minima of f. And therefore, option A is the correct answer. Now let us also explore the other options. They are mathematically very interesting, and we will actually prove how these other options are wrong. B option says that f is continuous at all rational number. Let us disprove it. A counter example can be constructed from part A. Consider y in a delta neighborhood of a non-zero rational number x, as we saw in the previous part. We saw that if y is not equal to x, then there are two cases. The first case is if y is irrational, then in this case, the difference between f of x and f of y is equal to modulus of 1 minus 1 by p naught, which is equal to p naught, which is a positive number independent of y. And in the second case, when y is a rational number, the difference between f of x and f of y is equal to f of y is 1 minus 1 by p, where p is a natural number greater than p naught, and this difference turns out to be greater than or equal to 1 by p naught plus 1 minus 1 by p naught, which is also a positive number independent of y. So the difference between f of y and f of x is a fixed positive number, which means that f is not continuous at least non-zero rational numbers. Now option C says that f is not continuous at all irrational numbers. Let us disprove that. We shall prove that it is indeed continuous at irrational numbers. For that, let us consider any irrational number x and an epsilon positive. By Archimedean property, we can get a natural number p naught such that p naught is greater than 1 by epsilon. Now this implies that taking reciprocal both sides, 1 by p naught is strictly less than epsilon. This implies 1 minus 1 by p naught is strictly greater than 1 minus epsilon, which implies that 1 minus 1 by p naught is in the epsilon neighborhood of 1, and 1 is the value of f of x, which means that 1 minus 1 by p naught is in the epsilon neighborhood of f of x. Now to prove the continuity of the function at f of x, let us consider delta positive for this given p naught as in part A and B. What happens is that if you take any y in this delta neighborhood of x, then we have the following. Case 1, y is irrational. In this case, f of y is also equal to 1, which is equal to f of x, and hence f of y is in the epsilon neighborhood of f of x. Now case 2 is interesting. In case 2, y is actually a rational number of the form n by p, where p is by construction greater than p naught. This implies that f of y is equal to 1 minus 1 by p is strictly greater than 1 minus 1 by p naught, and we know that this belongs to this epsilon neighborhood of the function. Very well. So combining case 1 and case 2, we have proved that f of y belongs to the epsilon neighborhood of f of x for all y in the delta neighborhood of x. This by definition means that f is a continuous function. So C is also wrong. D is an interesting exercise I'll leave for you. Here's a hint. Choose a delta positive for suitable value of p naught. And what that p naught is the exercise. Once you get that, this problem is a done deal.